The last category of bonds are metallic bonds. In metallic bonds, we have sharing, but a different type of sharing than what occurs in covalent. Metals tend to have low electronegativity values. So when we come over here, our metals are basically here and to the left, including tin and lead, etc. So if we were to look at the electronegativity difference between any metal with another metal, the difference would have to be about 1 to 1.2 or less, meaning that is not a strong enough attraction for one to gain and one to lose. The big difference here is that electronegativity in all of those is fairly small. That means that none of them attract the electrons very strongly, or there is not a quote unquote desire to pull more electrons in from any of them. So the electrons, because they're weakly held, do not stay on an atom, do not get shared equally between atoms, and are not gained and lost between atoms. They kind of float around in a free flowing, we often call it sea of electrons, and we also use the term delocalized, that they're spread out and they're moving around. That only happens in metallic bonds. Every now and then you'll see a little bit of a nonmetal mixed in, but if it is described with metallic properties or that sea of electrons rather than sharing or gaining or losing, we consider that a metallic bond. So we have our cation, or our central part of our atom, our nucleus and our inner electrons are held tightly. Those 1 to 2 valence electrons, and sometimes a few more than that, 3 to 4, are more free moving, and that free moving still attracts the cation to the electrons to the cation, but not holding things in the same way. So for all of these types of bonds, we initially talked about as a spectrum between perfectly gaining and losing and perfectly sharing. We set up borders around 2.0 for where it becomes ionic, around 0.4 for where it becomes nonpolar covalent, containing metals and only metals for metallic. But really there is a better representation right here, where if I look at how big the electronegativity difference is, and I look how big the average electronegativity of the two elements are, it gives me a good indicator of what type of bond I would have. So we still see mostly metals and nonmetals here, with a few very near the border of covalent. We see covalent as a lot of nonmetals with nonmetals. And then over here, we see metals with metals in the metallic bonding. So the type of element is a good indicator. Difference in electronegativity is a good indicator. Properties are the best indicator, because there's a lot more going on than just one factor contributing to what happens to the electrons. But what those electrons are doing determines how the compound as a whole will act and react, which is why the properties are so helpful.